shall we get started? How many of you are doing projects that involve convolutional neural nets? Okay, good. So today we're going to talk about different architectures, and maybe if we have time, I'll talk about a little bit about visualization. So far, we have seen the basic operations that are used in convolutional nets. New operations, I should say, so they're convolution, pooling, and batch normalization. We looked at a very simple architecture, LeNet, and confirmed that it actually does a lot better than a regular fully connected neural network in digit recognition. We saw the equivalence of convolutions and matrix multiplication representationally. One can be used to implement the other. We saw the back propagation, going in the opposite direction of convolution, and I guess that's about it. So, any questions about all of the basics that I have introduced so far? So, if you have any questions, now is a good time to ask, because then we're going to basically put all of these things together in different combinations to make more modern architectures. And of course, the ever-present dimensionality calculations, right? So you should be able to, given any complicated convolutional neural network, figure out the dimensionalities of all the weights and all the activations at every level of the network. Okay, so if there are no questions, let's start talking about architecture. So far, we've seen only one architecture, the LeNet architecture, and I defined it up here somewhere. Where is it? There. So this was the LeNet model from 1990s. It had two convolutional layers following an input of 28 by 28 by 1, and then two fully connected layers. And all of the convolutional layers had the same order of operations: convolution, bias, activation function, and pooling, in that order. Okay? Now, that is not the only way to design these things. First of all, we can obviously change the number of these layers. Instead of two convolutional layers, we can add more. And also, we can basically change what's done in each layer. So we'll see examples of both in today's lecture. So today's lecture comes from Stanford, so I should thank Stanford people for making this up-to-date, pretty much up-to-date review of modern CNN architectures public, because this is a fast-changing topic, and the lecture notes that I prepared 2 years ago are already out of date, because within the last 2 years new architectures were introduced. So I'm going to use these slides, which are mostly up to date. All right, so here's LeNet, as we mentioned. So we can recognize in this representation. So this is the first 5 by 5 convolution operation, giving us basically a number of plates of activations. Can anybody tell me how many plates there are in this first layer? The number of channels in the input was 1. The number of channels in the first convolutional layer was 20, I think, yeah. And then, so basically, if I did this figure fully, then there would be 20 of these plates, right? So every plate here represents one filter going around the whole image and giving us particular outputs. And there's 20 of them. So we pooling operation subsamples them, gets them from 24 by 24 to 12 by 12 by max pooling. And then we do another convolution. This time we have 50 of them, 50 plates, followed by another pooling And I'm not counting the bias and the relu operations, so every time you do this, there's also the bias and the relu. And then there's a couple of fully connected layers ending with the output. Any questions? So let's look at AlexNet. AlexNet is the 2012 winner of the ImageNet competition, which started this whole big interest in neural network architectures for image processing. It is mostly similar to GoogLeNet, except it's deeper and bigger, and it has these additional layers called the norm layers. So convolution 1 and max pool 1 are operations that we already know. Norm 1 is an example of a normalization layer, which basically, I think AlexNet used local response normalization, or LRN. We're not going to talk much about that because it's no longer used, and other people came up with architectures that don't use normalization. So the only commonly used normalization these days is batch normalization. So that's the only thing you're responsible for in this class. So this is an old meaning like 5-year-old normalization operation there. Convolution to max pool 2, another normalization layer, and then 3 convolutional layers on top of each other without any pooling in between. Each one followed by, of course, bias and relu, but no pooling. And then after a final pooling operation, we have 3 fully connected layers. So it's sort of an overblown GoogLeNet model. So I want to basically quiz you on your dimensionality calculations a little bit. So if you have paper and pencil, get them out. So with MNIST, our inputs were 28 by 28 by 1. With ImageNet, the inputs to AlexNet were scaled to be 227 by 227 by 3. Now the first layer that we called comp1 has 11 by 11 convolutional filters. There are 96 of them. And unlike GoogLeNet, we apply these things using stride equals 4. What was the default stride for convolution? 1, right? What was the default stride for pooling? Size of the window, exactly. So here, this guy is applying 11 by 11 filters at stride 4. So the question is, what is the output volume size? After this first convolution applied to the input of 227 by 227 by 3, I get an output volume out of this convolution. What is the size of that volume? What are the spatial dimensions and what is the channel depth? I'll give you 1 minute to figure it out, and then we can move on. You could ask me questions too if you're forgetting anything. Yeah. No, I just gave you a calculation of some sort. Whether or not that calculation is meaningful to answer this question, I don't know. Okay, so who has an answer? Show of hands. Okay, what's the other people doing? I want everyone to have an answer by now. We have a midterm coming up. And this is my favorite type of question because it's easy to grade.
Is special dimension 54 times 54?
Well, it's 55, but close enough. Okay. You may have made a floor-ceiling type of error. It's close enough.
Yeah.
And the depth is? 96 because we have 96. Yes, so the answer is 55 by 55 by 96. Next question, number of parameters in this layer. So this is a convolutional layer. I have 96 filters that are 11 by 11 each. So how many floating point numbers do I have to store for these parameters? Yeah,
96 times 11 times 11.
11 times. What was the last one?
3.
3. Why is the last number there?
Because there's 3 channels.
That's right. So there's 3 input channels. And remember how convolution works. Convolution works by applying an 11 by 11 filter window, but it also has a depth 3. The depth of the convolution matches the depth of the input. So one of our filters is basically 11 by 11 by 3. And then we have 96 of them, so we have to multiply all these numbers to get the number of weights in this layer. So 35,000 parameters in this layer. All right, so after the convolution, we apply pooling, and this is also a bit unusual in the sense that it's not using our defaults here. So we have 3 by 3, I shouldn't say filters here. Window size is 3 by 3 for this pooling operation, but stride is 2. By default, the stride also would have been 3, but AlexNet uses stride 2. So after this pooling layer, remember after comp1, our activation was 55 by 55 by 96. After the pooling, what do I get with this window and stride? Again, you can use the hint. Anybody brave enough to guess an answer?
Let's say right 27.
Correct. So 27 is due to the reduction of the pooling layer in the spatial dimensions, and 96 because pooling does not touch the number of channels, right? So every channel is pooled independently of the other ones. So we have 27 by 27 by 96. What's the number of parameters for this pooling layer? It's a trick question. Yes, it's 0. Pooling layers don't use any parameters, or at least not learnable parameters. We can say, okay, so window size and the stride, but those are integers and they're not actually updated during training, so we don't count them as parameters.
When you don't specify anything, do we just assume it's an average pool or a max pool?
Max. Default is max. Okay. So here's the rest of the exercise. You should be able to calculate all of these numbers yourself. So we go from 227 spatially to 55 to 27 to 13 to 6. At the end, before the fully connected layers, we have 6 by 6 by 256 inputs, 256 channels, and then we have 2 fully connected layers with 4096 hidden layer size each, and the final layer has 1000 outputs because there is 1000 classes in ImageNet. Any questions? Yeah.
So, I think the convolutional networks were there till early 90s, right?
That's correct. This was the first large-scale victory for them. So GoogLeNet is from the 90s, but GoogLeNet basically was able to recognize handwritten digits, which are 28 by 28 grayscale images. And here we're talking about a decent resolution photograph, and we're talking about recognizing any one of 1,000 categories in this photograph. So nobody, well, almost nobody, up to 2012 actually thought that just training a deep enough neural network would actually succeed in this problem. All the other competitors actually had hand-built filters and well-engineered systems, etc. But AlexNet, trained on this problem, reduced the error rate significantly.
It's
Yeah?
What's the score of AlexNet competition?
15% top 5 error rate. The best scores before that was almost twice as high. Okay, so in ImageNet, one of the scores they cite is the top 5 error rate, which means you're giving probabilities to all these classes. If I take the top 5 guesses that you make, is the correct answer among the top 5. So if it's not, I count that as a mistake. So AlexNet was able to do 85% with this measure. Other details is ReLU, the most popular activation function today. AlexNet was the first system to use it. The norm layers are not used anymore, as we mentioned before. They actually did heavy data augmentation. What does that mean? Even though the training set contained 1 million images, AlexNet was not satisfied with that. It took those images and it shifted them a couple of pixels, it added some noise, it did all sorts of other transformations to increase the dataset size. They use dropout, the training, a popular training option for these types of deep nets is SGD with momentum, which I will explain in a future lecture, all these different variations of SGD. But basically in a single sentence, SGD with momentum says, don't just move in the direction of the current gradient, but remember the previous gradients as well, and keep some of the momentum for those previous gradients, and do some sort of averaging. Okay. Learning rate, if you don't know anything, always start with 10 to the minus 2. Okay, so which they did, and then reduce tenfold each time the accuracy plateaus. So that's also a very common technique. So the initial learning rate that you start with might lead to large step sizes, which are maybe necessary in the beginning when you're far away from the solution. But as you get closer and closer to the solution, you might want to actually reduce the error rate to slow yourself down. Now, I don't want you to have the impression that you have to have this, because it's going to happen automatically. Let me show you why. So if you're actually optimizing a function like this, a simple function like this, over here, the gradient is going to be pretty large. Okay? So if I'm using a particular learning rate of 0.01, I'm going to take a step that's 100 the size of this arrow, let's say. But as I get closer and closer to the minimum, which is here, the gradient itself gets smaller because the slope is less. In fact, at around the minimum, the slope is 0, right? So the gradient itself is actually getting smaller and smaller. So even if you don't slow yourself down by reducing the learning rate, your step sizes are going to automatically go down if you're optimizing a function like this. Okay? Now, it's not always clear if you're optimizing a function like this. Most deep networks seem to be a lot more complicated than simple convex function optimization. So slowing down might help, but I just wanted you to know that for nice behaving objective functions, the slowdown occurs automatically. They also used L2 normalization, which by now you know what it means. So it's basically adding some multiple of the L2 norm of all the weights to your objective to keep them small. And finally, they used ensembling, which is the last trick that everybody uses as the last step to get to squeeze out the last few % of performance from these networks. So ensembling means you independently train, in this case, 7 different networks, starting from different random initializations, and then during test time you use them together and you average their output. Okay, and that always gives you a 1-2% boost. no matter what the problem is, almost. So using that, their error went from 18% to 15%, for example. Okay. Any questions? So that was AlexNet. You should be able to build this thing, except for the LRN normalization layers. Everything in this network is buildable with a few lines of code in KNet that you've learned so far. Actually, that's true for all the architectures I'm going to talk about today. In fact, I was actually going to sit down and build a notebook for you guys, but I got busy, so maybe one of you will work on that and donate it to the class. Okay. One little detail. AlexNet was trained in 2012. Back then, I don't even know if CUDA existed. Did CUDA exist in 2012?
Yes, 2006.
Oh, okay. So CUDA was there. Okay. But you know, large GPUs weren't there yet. So the GPUs they used only had 3 gigabytes of memory, and it didn't fit the network and the activations for training. So they used a 2 GPU machine, and they actually split the model on the 2 GPUs. In the first couple of layers, actually, they split it from channels. So if you're actually going to output 128 channels, they basically put 64 of these filters to GPU 1, 64 of them to GPU 2, and then they actually kept moving like that on the 2 GPUs, divided from channels. Now, is that the same thing as doing everything on 1 GPU, or do you see a problem with this? Well, if I have 96 channels, or 96 is my output of the first convolutional layer, I put 48 of them, 48 filters in one, and 48 filters in the other. And they both start with the same input and output their corresponding results. Is that output identical to the output of doing this in one GPU? The answer is yes for the first layer. But then what happens in the next convolution? In the next convolution, now GPU 1 only has access to the first 48 channels. GPU 2 has only access to the second 48 channels. Okay? So in the next convolution, unless you basically bring them together, then you know some channels are going to only see some other channels, etc. Okay? So it's not exactly the same. So for the first couple convolutions, they moved separately like this, and then at some point they started communicating with the GPUs and sharing information. And by the time you got to the dense layers, I believe you... so there's that complication as well. So if you try to replicate this on a single GPU, which you can these days, you may get slightly different results because of that. Right, so these are the layers where the GPUs were split, and these are the layers where there was communication across GPUs, so we brought the different channels together for the next layer. All right, so let's go to history. I don't know why they drew this graph backwards, but the time moves toward the left. So over here, 2010 and 11, we don't have convolutional nets. 2012, there is an 8-layer AlexNet. This is the first convolutional net-based winner. In 2013, we had a variation on AlexNet, basically keeping the same number of layers and operations, but playing with the hyperparameters. They optimized it further and achieved another 5% reduction in error rate. And 2014 had 2 very close winners, very famous these days, called VGG and GoogLeNet. They use different methods, but they both increased the depth from 8 to, as you can see, about 20, and they almost halved the error rate as a result. Both of these things are still used, especially their last layers. So when you actually do a CNN-based project, so let's say you want to look at this room and recognize some cups and laptops and some chairs and whatever, you don't start usually training your network from scratch, because that takes days, okay? So you take an already existing pre-trained network from that won the competition in the last few years, okay? And you chop off the last few layers, because those were specific to the ImageNet categories. But hopefully, the previous layers are doing some generic image processing, and they should be able to be repurposed for your new task. So you freeze the, that portion of the net, you retrain the last few fully connected layers for your own task, and that's how people usually apply these things to new problems. Okay? So, for the purposes of in the papers that you've picked, this method might have been used, in which case you're lucky because you don't have to train the whole thing. But if you are going to train the whole thing, please start early because it takes time. And then starting 2015, things got crazy, and we have hundreds of layers now, and we'll come to that in a little bit. So yes, that was ZFNet, which was the hyperparameters. Here is ZFNet. It's pretty much the same, but the first convolutional layer changed from 11 by 11 to 7 by 7, and then the number of the size of the other convolutional layers changed. I think they stopped using normalization as well. Basically, fiddling around with it some more. Okay, got them another 5%. So let's look at the VGG and GoogLeNet now. Yeah.
Did anyone train AlexNet with one GPU, like the same network?
I'm sure they have by now. Because AlexNet is available in a lot of different frameworks like PyTorch and okay.
And any improvement over the 2 GPU error?
On ImageNet?
Yes.
I don't know.
Because I'm thinking 2 GPU is maybe mimicking 2 hemispheres of the brain somehow.
Also, there's an interesting analysis of that actually in the paper. And if you look at the low-level filters on the 2 GPUs, they do tend to sort of, I don't know, one sort of detects edges more, the other one detects colors more. So there was some speculation in that direction, I think.
Would decreasing batch size help in fitting everything into one GPU?
Yes, so basically in these big networks what we do is you do these calculations, that's why I'm basically torturing you with all the dimensionality calculations, and as a result of these calculations you get the total memory cost of your model and total memory cost of processing a single image. And then double that because there's also going to be a backward pass which doubles all the memory requirements. And from that you can basically guesstimate how many images you can fit, and that's how you determine your batch size. Okay? Okay, so let's talk about VGG first. It's the simpler one of the two. So from compared to AlexNet and ZFNet, it uses the same components, a bunch of convolutions and pooling, no normalization. Two main differences. One, it's deeper. AlexNet has 8 layers. VGG has different versions with 16 layers and 19 layers. That's one difference. Another difference is AlexNet has lots of different types of sizes of filters. So it starts with 11 by 11 and then goes to 5 by 5 and then goes to 3 by 3. VGG is very, very uniform. Every convolutional layer has 3 by 3 filters. They don't use anything else, okay? With stride 1 and padding 1. And every pooling layer is just a regular standard 2 by 2 pooling with stride 2. So you can, I don't know if you can read this, but from the colors, the orange things are convolutions. So 2 convolutions after the input plus pool, 2 convolutions plus pool, 2 convolutions plus pool, and then 3 convolutions, and then the last 3 layers are the fully connected and softmax layers. So very, very simple, just deeper. Okay? And using this deeper network, they were able to get the top 5 error rate to below 10%, at around 7%. Now, let's think about the smaller filters and their receptive fields. Okay? So, let's compare a 7 by 7 filter applied to the original image with a couple of layers of 3 by 3 filters applied to the same image. Okay? So the receptive field of one 7 by 7 filter in the first layer is obviously 7 by 7. That's the window size it's looking at. On the other hand, in the first layer of VGG, the receptive field is 3 by 3. My question to you is, what is the receptive field size on the second layer of VGG? Namely, each neuron in the first layer of VGG is connected to a 3 by 3 patch. Each neuron in the second layer is connected to what? Indirect.
9 by 9. Like in a sense.
Think about strides.
Sorry.
So let's draw this together. So let's say this is the receptive field of one neuron in the input layer. It's a 3 by 3 pixel receptive layer, right? Now where is the next one? Well, the next one is here, because it's stride 1, and the next one is here. That's also stride 1. And going down, and going up, whatever. Here's the next one going up. Here's the next one going up. So these are the neighbors of this guy, right? So if my starting neuron has this receptive field, its right neighbor has this receptive field, which is 1 pixel shifted to the right, and its right neighbor has this one, which is 2 pixels shifted to the right.
Is that 5?
Yeah. So then, in the next layer, a single neuron has access to a 3 by 3 grid of these neurons. Right? So a 3 by 3 grid of these neurons is going to cover this much space, which is 5 by 5. Is that clear to everyone?
What about max?
In VGG, we have like convolution layers one after the other. Only after a certain number of them we do pooling. Now, what about the third layer? If I add another 3 by 3 convolution?
7 by 7.
7 by 7. So at that point, I have the same receptive field as the original 7 by 7 convolution, right? Is there any difference from a representational point of view? Is there something that this triple layer small filter architecture can represent that the 7 by 7 cannot represent? Well, 7 by 7 convolution is a linear operation, right? It just multiplies the pixels with some numbers and adds them up, etc. Whereas if we have 3 layers on top of each other, 3 by 3, between each layer we have a nonlinearity, we have ReLU between each layer. So we're applying at least 2 layers of ReLU in the triple deck thing. So representationally that might be more efficient in capturing certain patterns because of these nonlinearities. Okay, even though the receptive fields are the same, the types of patterns they can represent might be richer. How about weights? So what is the what is the number of parameters of a 7 by 7 filter applied to the input? One filter. 49 times 3, right? So there's 3 depth.
Ah, yes. Yes.
Right, a single filter is going to be 7 by 7 by 3. How about in the case of the other one? We basically have 3 filters, one after the other. Each of them are 3 by 3 filters. And what would be their total weight, number of weights? So let's see. So okay, so if we call C the number of channels per layer, so let's say, yeah, we don't know C because in the beginning it's 3 and then soon it becomes 256. So let's assume we have C channels at every layer. If we have C channels at every layer, then a 7 by 7 filter is going to be this size, 7 squared times C squared. Why? Because it's 7 times 7 times input channels times output channels, which are both C, we're assuming. Okay? Whereas 3 layers of 3 by 3 filters is going to be this much, right? So each layer is going to be 3 by 3 times C by C. And we have 3 of them. So what is this? 49C squared, and this is 27C squared. So you actually use less parameters in the 3 by 3 case, stacked 3 by 3 case. Okay, so here's a calculation, some memory calculation. I don't know if you can read this all, but you should be able to do this if asked. So let's see what this is calculating. So here's a layer, convolution 364. Okay, so it's the size, the volume that it's working with is 224 by 224 by 64. So that means the memory that it takes is 3.2 million floating point numbers per image. Okay, so 3.2 megabytes per image is going to be spent on this layer. Double that if you're counting the backward pass. And to represent the filter bank, we need to have 3 by 3 by 64 by 64, 36,000 parameters. Usually the number of parameters are not the actually I'm going to not say that because it's not true at every level. So let's see. This is the input, this is the output, right? So input starts from the top, and notice that in the input area, the actual, well, there's 2 sources of memory expense, right? So GPU memory has to be used to store our parameters, but only 1 copy of these parameters. You don't need more copies of these parameters, right? So maybe, okay, 2 for gradients, 2 copies at most. And images that we use in a mini batch and their activations, all the way forward and back. Again, 2 copies of these things. And the batch size basically says that we can have as many multiples of this image memory. So if you look at it in the beginning, the image memory, the image-related memory, the activation memory is 3.2 million, whereas the parameters is 36,000. Toward the end, my activations became much smaller. I'm talking about now 14 by 14, right? So I went all the way from 224 images to 14 by 14 images. I have more channels, but still, the total number of floating points that I need to represent this image is 100K. It used to be 3.2 megabytes. But the parameters now, since I have a lot of channels, grew to 2.3 million. So now I'm actually using more space for parameters. And Most of the parameters in this model is spent, parameter memory is spent on the fully connected layers. Look at the fully connected layer. So the first one has 100 million, the second one has 16 million, and the third one has 4 million. So those easily wipe all the other convolutional parameters that we're using from before. This is one of the reasons why modern networks no longer use fully connected layers, because they take too much space. Okay. Any questions about these memory calculations? So each time you're working with a convolutional net or any large memory hog model, you should always have back of the envelope how much space for my parameters, how much space for my images, how many images can I fit in a mini batch without exceeding the GPU memory. Those things should always be at the back of your minds. Yes?
They are using, are they using padding in the convolutions? Because
Yes.
that's what
Filter size 3, padding 1, so that consecutive convolutions don't actually change the size, don't change the spatial dimensions. So spatial dimensions only change during the pooling operations. Okay, so total memory is 96 megabyte per image, and total number of parameters is 138 million. Yeah.
Why do we double the number of parameters? Aren't they updated in?
Yes, but I need to keep their gradients somewhere. So the gradient calculation going backward means that for every array that takes place in the calculation of the loss, we'll create an equally sized array representing the sensitivity of loss to each of these array elements. So behind the scenes, when you use grad in KNet, or when you do it by hand, explicitly, you have to have an equal sized array for every forward array to calculate the backward gradients. Okay. So VGG is very popular because it's very simple. It's very, I mean, it's like five lines to implement in KNet. And you can download its parameters, train parameters from the internet, and immediately start classifying some images. Did I actually show you the VGG demo? I probably did in the first lecture. We can classify some elephants and flowers and stuff. No? Let me fire that up. Shut this down. Here's the VGG example. And okay, run all. Okay. This will run in the background while we look at the next. So other differences: no normalization layer. VGG 19 only slightly better. Uses more memory but gives you another % or so. Again, they use ensembles for best results. And they use FC7 features for other tasks, just like I was talking about using existing models for other tasks. So you take this whole VGG16 network, you ignore the softmax layer and the fully connected 1000 layer before it, and that leaves you with this last layer, FC7, which has basically mapped all images to a 4096 dimensional vector, and you can take these vectors and do a lot of other tasks with them. You can train them to recognize other things in that image, etc. And VGG generalizes particularly well to these things. Okay, so there is the our picture, and here's the VGG, which is hopefully going to classify this picture as an elephant soon. Yeah, so So there's the output. This is the top 5 output. The numbers on the left are probabilities, and the strings on the right are the class strings. So that picture was classified as an Indian elephant. So you can go to this page, run it up on your laptop. You don't even need a GPU. Cut and paste any image from the internet, or give the URL as an argument, and you will see the output of the VGG model using this node. All right, so next we're going to talk about GoogLeNet, which is very different compared to the other models that we've seen so far. So it has 22 layers if you count all the convolutional boxes as layers. It actually created, they were basically thinking about how to reduce the amount of memory and the amount of computation by designing something smarter than, convolution bias activation function pooling. Okay, so that was the standard until 2015, when Google started, okay, maybe we shouldn't, do these operations in that order. Maybe there's a better way to connect these boxes together that will actually be able to learn the same function with fewer parameters, fewer computations. As a result, they actually they came up with this module that they called the Inception module. I think there was a movie called Inception that year. Probably that's why they named it that. No fully connected layers. The whole thing only has 5 million parameters. That's 12 times less than AlexNet, even though it's much deeper and it does a lot better. Okay? And it got 6.7% top 5 layers. So I just want to talk briefly about the motivation behind this Inception module. How did they come up with this thing? So the original motivation is, we don't know what we want to do to the previous layer. We don't know if we want to apply a 3x3 convolution or a 5x5 convolution, or just pool this thing. So let's do all of these things together and then combine the results. Okay, so that's the first motivation. So you get some sort of volume from the previous layer, and then you apply a 1x1, 3x3, 5x5 convolutions to it, and you also apply no convolution at all and just have a 3x3 pooling in parallel. You apply all these 4 operations in parallel. Each of them give you, and you do the padding so that the spatial dimensions don't change. Okay? So each of them give you some number of channels with the same spatial dimensions. And then you concatenate all those channels together. So all this information is somehow kept within the channels of each pixel, the results of all these different operations. Okay, so that's the original idea. But this happens to be a bit expensive. How expensive? So let's say, as an example, I have this many 1x1 convolutions, this many 3x3, this many 5x5, and there's this pooling here. And my input, let's say in the middle of the model somewhere, is 28 by 28 by 256. Okay? So, again, let's return back to our quiz. What is the output size of the first box? 1x1 convolution with 128 filters. 1x1 convolution is an interesting operation. I would encourage you to think about that and how to use that. We use it a lot in our sort of grounded language learning type cases. So 1x1 convolution means you have an input 28 by 28 with a certain depth. Your convolutional filter is like a little pencil going all the way in the depth dimension, but basically looking at a single location, looking at a single pixel, but for all the depth. So you can use that to, for example, pick locations in the image where a particular channel is especially hot, or there is a certain pattern in the channels. Right? So it's basically a channel filter. It highlights the pixels that match a particular pattern of channel activations. So what is the output size of the first box? Output size of this box?
28 by 28
by,
by 2, 5, 6 times 1 through 8.
no. So first of all, I want three numbers from you because it's a volume. So a volume comes in, a volume comes out. Even though we always talk about four numbers, the fourth number is for mini batching. I'm not assuming any mini batching for it. Yeah, 128, because this number is the number of output filters or output channels, right? So same dimensionality, the number of channels reduced to 128. Okay. So let's look at the sizes of the other ones. So they're all 28 by 28, as I mentioned before, because we're basically padding things enough so that the spatial dimensions don't change, and then the number of channels is given by each box, except for the pooling box. The pooling box does not change the number of channels. Okay. Here they're probably using a stride of 1 and a padding of 1 so that the size doesn't change. So first of all, space-wise, this can only increase my input size, right? So first of all, the output and the input have the same spatial dimensions. I didn't reduce anything using pooling. So the output is still 28 by 28. But the number of channels increased. Why? Well, because even the pooling layer has the same number of channels as the input, so it can only increase. So if I use these modules, my channel number is going to keep increasing and increasing. Okay? So what's my output size after I concatenate filters? Final output size? Yes, 28 by 28, and then add up all the third numbers together, and that's the number of channels you have. That's right. So it happens to be 672. So I went from 256 to 672. Let's also count the number of operations. So, for example, for this operation, how many multiplies do I have? So I have 128, pencil-shaped filters that go the whole depth of the image, which is 256. So each of these pencil-shaped filters have 256 dimensions, right? So to get the output of one of these things for one pixel location, I need to do 256 multiplications first of all. Okay. And then I need to repeat this 28 by 28 times for all the pixels. So that's one filter's output map. And I have 128 filters to start with, so I also tried 128 times, so the total number of operations is given right there. And if you add this for all of the different convolution operations, it turns into 850 million operations to get through this one layer. Okay, so how can we solve this problem? They basically came up with these things called the bottleneck layers that use one-by-one convolutions to reduce feature depth. Okay, so generally when we want to shrink the input, up to now we always use pooling. Pooling shrinks everything in the spatial dimensions. Okay, what should I do if I don't want to shrink in the spatial dimensions? I want to stay at 28 by 28, but I want to shrink in channel dimensions. Okay? I don't want my channels to keep growing. Well, what I can do is I can take an image that has a channel depth of 256 and then map it to a compressed image that has the same spatial dimensions but a channel depth of 128 using 1 by 1 by 128 filter. Right? So the output of a 1 by 1 convolution is basically a shrinkage. It can be seen as a shrinkage of the channel dimension. I can basically grow or shrink the channel dimension any way I want using a 1 by 1 convolution. So these are called bottleneck layers. So they basically, so here's an example. So if I start with 56 by 56 that has 64 channels, apply a 1 by 1 convolution with 32 filters, I basically get the same sized output with 32 channels. Any questions about this?
can we shrink them to any other number of
Yeah.
that one?
Because you decide how many filters you have, right? So if you have 32 filters, the channels will be 32. That's a number that you're basically putting there. And presumably, whatever is valuable in your input for the task that you're trying to solve are the combinations or linear combinations that this filter is going to learn to preserve in these 32 channels. Okay, you start with 64 channels, but presumably there's a lot of redundancy. Not all these 64 numbers are independently relevant to you. So you learn a way to linearly combine them to 32 numbers instead.
Can we
Yeah.
go back from that 32 to 64 with some kind of...
With information loss, of course. You can't go exactly,
Yes, of course.
but with some information loss you
You
can.
can say it is actually a type of compression.
Correct. Yes. So task-specific compression. The goal is not just to shrink your input, but to shrink it in such a way that your task accuracy doesn't get negatively affected. Yeah.
I didn't quite understand when you said learn to decrease the number of filters.
Because these one-by-one convolutional filters are all learned. You don't hand-build them.
But like the 61 was the hyperparameter that we started, right?
Right.
So,
And 32 is another hyperparameter.
so when we decide to eliminate a filter, right?
We're not eliminating any of the channels, we're just linearly combining them into new channels. Because imagine each of these one-by-one filters is like a pencil going 64 depth. You take a dot product, that gives you one of the numbers out in this box. And, you know, so for each number out in that box, you can decide what that dot product is going to use as a filter.
So we have like 64 times 32 weights here, right?
Right, so the weight of an individual filter is 1 by 1 by 64 by 32. Okay, so if I sprinkle some of these dimensionality reducing bottleneck layers in my naive inception module, I get to the actual inception module they're using. Okay, so the first one doesn't change because it's already a 1 by 1 convolution. In the second layer, before I get to the expensive 3 by 3 convolution, I first reduce the number of channels using a bottleneck. Here, before the expensive 5 by 5 convolution operation, I reduce the number of channels using another bottleneck. And here, after the pooling, which is not a very expensive operation, I reduce the number of channels using a 1 by 1 bottleneck. And this pattern, among all the patterns I'm sure they played with and tested, happened to work well as an individual unit to build the GoogLeNet. They call it the inception module. Okay, so now we can actually recalculate all the things that we did before. And previously we had 854 million operations. In this new module we have 358 million operations. So we can cut the number of operations in as much as we want, but you know, they cut it in half. And also the number of parameters is also cut, right? So if your input channels is smaller, you don't have to have that many parameters in the filters. Yeah.
Should I have to do this 1 by 1 convolution to this previous layer 3 times, or just you can just 1 times that?
That's a good point. They did it 2 times, presumably thinking that the filters that you need before the 3 by 3 convolution might be different than the filters you need before the 5 by 5 convolution. But you could certainly define a inception module merging these 2 things together and see if it makes any difference in the performance.
Is there any problem?
No. So any type of module that you can imagine almost, as long as it consists of differentiable operations, the KNet grad function can handle.
What about using random 3x3 convolution, why don't we use less number of filters?
The output filters, that's another way to reduce the dimensionality. But if we don't use any bottleneck layers, as I mentioned before, you can never reduce the total number of channels, because on the right side, as a result of this pooling, you already have 256 channels. So if you don't want your channel number to keep growing, at some point you need to do something about it. And these guys solve that by putting these bottleneck layers in there. Okay. And then once they basically discovered this module was nice, they stacked a bunch of them together. Now, there's another important innovation that they actually came up during training, and I don't know the exact contribution of these two ideas. Maybe they specified in their paper, we should look. So the second idea, it doesn't relate to the architecture, but to the training. So one of the problems with training very, very large, deep networks is that the gradients in the backward pass might shrink, and because of floating point errors, you know, they might disappear, they might not be effective. Another way to think about it is basically you have a very, very deep network. Here's the input, there's the output. If I wiggle one of the weights here, the output is not going to change too much. And that's basically the definition of gradient, right? So what they did to solve that is basically they took outputs in 3 different places in the network, okay? So they take an output over here, so all these things that go to the side with a bunch of fully connected layers are additional prediction paths. So they make a prediction after this many inceptions, they make another prediction after a couple more inception modules, and they make another prediction at the very end, okay? And during training, they average all these predictions, so the loss comes from 3 different paths going backward. So that means in the original network, the weight over here was really, really far away from the loss at the very end. But now it's actually relatively closer to the loss that comes from this decision. So now I have a sizable gradient, and I can basically use that gradient to converge more effectively. So that was the other idea they introduced. Now, for example, if you take this idea and apply it to VGG, would it also improve the training of VGG? I don't know. These are things that you can play with. Yeah.
So double counting doesn't really make a problem because the
I'm not double counting anything.
no, but aren't you like the weights at the bottom?
I define the loss any way I want. So, right, so I give some input to my network, it gives me some outputs, and then I can define loss on any number that has been generated by my network. So here, I basically decide I'm going to take the correct probabilities and compare them with 3 different probability vectors at different places in my network, and add all of these things up. It's a loss function. I can define it any way I want. Now, whether or not you also do this averaging during test is up to you. And I don't know the details of that. So they may or may not have done averaging over these 3 decision regions at test time. These are they call them the auxiliary classification outputs. And their main purpose is to have better gradients in the early lower layers. Because unless you get nice gradients coming from the top, these early modules, which are supposed to calculate these important things like edge detectors and other filters, they don't get enough information from your training to converge to these useful filters. But if you do a very shallow decision output, if you take a very shallow decision output, they have more information and they converge earlier. Yeah.
Then the previous layers weights are mostly updated by the first additional loss
Yes,
function?
if we actually looked at the gradient coming back from these 3 different things which get added, at the end, you would probably find that initially at least this guy supplies most of the magnitude.
Then it's like I'm training the first form.
Basically, almost in the beginning, right? Which is better than not training them at all, because that's what normally would happen in the beginning. They would just randomly move. And at least you're giving them some sort of target to move toward, even though it's not the end target. It's a useful target to move toward. Okay. Now I want to finish talking about ResNet because it's the best one among the ones we talked about. So let's learn about ResNet. As you can see, there's two striking numbers in the ResNet box. One is this number, 152 layers. Okay, so we were talking about going from 8 to 20, but these guys just left everybody behind. And as a result, they have 3.5% top 5 error, which is supposedly better than humans. At least one particular human, Andrei Karpathy, which was in this group back then, actually trained himself to answer ImageNet questions and measured his own accuracy. And ResNet was better than him. Okay, so the big idea of ResNet is these residual blocks. And let me first tell you what a residual block is and then give you some motivation. A residual block looks like this. Basically, it's a regular two-layer convolution type of block, with the exception of this skip connection. Okay, so there is also a connection that ties the original input to the ReLU output. Okay, so with the exception of that arrow, it's just a regular couple of convolution blocks stuck together. Now, since I'm taking x and I'm adding it to whatever is the output, my final output from this block becomes x plus something. Okay, so this plus something, which is called f of x here, is the function computed by these two convolution boxes. So, in other words, what I'm telling to these convolution boxes is, instead of learning the actual function that you need to perform here, learn the difference that you need to make to this image, the difference from the original image. You don't need to learn to preserve the information in the image. I already did that for you. Just tell me how much delta from the image that you want to perform. Okay? So that's why it's called ResNet and residual block, because instead of learning the, I don't know, if we call the final output h of x, instead of learning h of x directly, we're only learning h of x minus x, which is the residual. Okay? Now that's nice, but why should that matter? Well, it matters because, again, when you think about gradients and the difficulty of passing gradients back, this line has a very nice property. The gradients flow back untouched through this line, right? So even if my convolutional layers are very deep, I have a direct connection through these skip networks all the way to the end, right? So when I'm thinking about the backward pass, so there's some error up top. This error is being passed backward. All these lines allow that signal to come unhindered. So there is no matrix multiplication through those things. There's no inverse convolution through those things. They basically just pass that error right back to me. So if I'm a poor guy in the input, which normally would have to wait a long time for the network to converge and for start getting nice informative gradients, now I don't have to wait. Because through this channel, I'm actually seeing the exact error up top. And it's coming back to me directly. So that's basically solving a similar problem where the GoogLeNet tried to solve using multiple outputs. Okay? So here we're using skip connections instead of multiple outputs in order to pass the gradient from the output to the early layers easily. All right? Now, one of the motivations that inspired ResNet was this. Do I have that graph here? Yeah. So when people first started experimenting with deep networks, they saw this puzzling thing. So here's training error, here's test error. There's a 20-layer network and a 56-layer network, let's say. Okay. Now on the test set, the 20-layer network is doing better. Now that's not too surprising because we say to ourselves, oh, you know, 56-layer network has a lot more parameters, so it's probably overfitting, and that's why it's not doing as good on the test set. But the surprising thing is the 20-layer network also does better during training. That's stupid because obviously the 56-layer network should do better. I mean, at the very least, the 56-layer network can converge 36 of its layers to identity, and then the other 20 would do as well as the 20-layer network. Okay? So obviously, that solution that gave 20-layer network this performance is within our search space. But unfortunately, since it's a very deep network and all these gradient-related problems, optimization problems, we can't find that solution. Okay? So this was the original motivation. You know, deep networks not only get worse test errors, but they also get worse training errors, which is a problem of optimization. And then, if you think about it, okay, so what did I just say? If I'm a 56-layer network, I should be able to replace 36 of my layers with the identity function, and the rest, the 20 layers, should be able to do as well as this. Now, look back at the ResNet architecture. Okay, so the ResNet architecture gives you the ability to turn this whole block into an identity function very easily. If I set all my convolutional weights to 0, this block is the identity function. So if I stack a bunch of these things up, and I start them with very small weights, initially they're all calculating the identity function anyway, right? So that makes a 56-layer network much easier to discover the 20-layer solution without getting lost in this optimization and small gradient problem, etc. So that's another sort of intuition to explain why ResNets can be so deep and can be trained to be better. Okay, so yeah, that's the story of that. The full ResNet architecture basically consists of a stack of residual blocks, and every residual blocks consists of 2 convolutional layers, again 3 by 3. They don't change the output size with padding of 1. And there's various numbers. You start with 64s, you go to 128s, you go to 512s, etc. And there's some pooling in the beginning, in the end. I don't know if in the middle. We also have a ResNet demo. Do we have a ResNet demo? I think we do. Yeah. There's our ResNet. So you can do the exact same thing that we did with VGG using ResNet. Let me shut this down so we don't run out of memory. And you can look at the actual Julia file to see how John had implemented this. Now, oh, that's another thing. So they don't use pooling. Yeah, I remember that correctly. They don't use pooling. Instead of pooling, they do strided convolutions. Okay, so if you do a strided convolution, then that also reduces the spatial dimensions. So every once in a while, they use a strided convolution to shrink the spatial dimension. There's an additional conv layer in the beginning to probably get the input size small. There are no fully connected layers because, as you know, they actually cost a lot of weights. So there is a single softmax layer that has 1,000 outputs They actually tried different depths on ImageNet, starting from 30 to all the way to 150. And for deeper networks, they also borrowed the trick from GoogleNet of using these bottleneck filters, the 1x1 filters that reduce the channel size. So this is a typical example where from 256 channels, I reduce it down to 64 channels using this bottleneck, and then I do a 3x3 convolution, and then another 1x1 convolution to get it up back to 256. So in the input and in the output, I have 256 channels, but when I'm doing this expensive convolution operation, I only have 64 channels. So that also speeds things up and saves you some memory. Batch normalization, we saw last lecture, it was used. Xavier initialization, which is also what we used in our CNN notebook. This was also initialized with Xavier, I think. Yeah. So this function actually gives you the Xavier initialization, which basically sets the weight magnitudes to a particular range determined by the number of inputs and number of outputs of this particular layer. SGD plus momentum again, like the other ones. Learning rate again starting higher, actually at 0.1 and reduced by 10 every time we stop improving. Mini batches of 256, weight decay of 10 to the minus 5, and they did not use any dropout. So this is also something that can be replicated fairly easily. And in 2015, they basically tried this on various competitions, COCO, MSRA, ImageNet, and they did, significantly better than everybody else. So currently, it's sort of the best option if you're going to take a network and use it for other purposes. I would start with ResNet. Okay. I think we're out of time, but I just wanted to show you this final slide. So this is the top 1 accuracy over the years of various models that we've seen. There is some here that are combinations of ResNets and inceptions. People are going crazy trying all sorts of different modules now to improve this even better. So at top 1, we're at 80% level now. This is a very nice graph. Basically, the x-axis is the number of operations you need to perform to process one image. The y-axis, it gives you the top 1 accuracy. So x is how expensive you are computationally, y is how accurate you are, and the size of the blob is your memory requirement. Okay? So as you can see, VGGs are very expensive memory-wise and computationally, and their accuracy is okay. GoogleNet that we've seen is tiny because it's much smaller than even AlexNet over here, but does a lot better. And we have a bunch of ResNets, 50 and 101 and 34. There is the Inception version 4, which is at the top. That's looking pretty good, which uses ideas from ResNet. So it does have residual connections plus an Inception-like module in it. So, and this is from 2017, so this is ongoing research. So any innovation you bring to this might be published and make you rich and famous. All right. Yeah.
So the operation that like the operation size kind of determines how long you're going to train, right? And
yes, partly. It affects that as well. But this was the test time operation size, I think.
But the memory requirements and the whether you can train or not, right? Because you might run out of GPU.
No, you can always deal with that, reducing your batch size. If you can't even fit one image, then you're in trouble. But usually the problem is not that bad. And the new GPUs have 16 gigabytes of memory, so you can actually do a lot more. and you have a friend who's working on multi-GPU solutions, so if your model is too big, he can fit it in 8 GPUs, so there is always solutions. But as you can see, I mean, more memory, spending more memory, getting a bigger model doesn't necessarily translate to performance in this thing. Any other questions? Yeah.
Hocam şu sorun.
Sure.
Inception modelde aynı gibiydi aslında fikir olarak. Residual. Yani sadece
Oh, Inception model did different sized convolutions in parallel and then combined their channels, all sorts of different things. Residual networks only do these skip connections.
Tanpet mesela unit'e paralel edilir. Yani residual bu.
That's true. However, that's also true for regular convolutional nets. A convolutional filter can just learn to be the identity filter. But the advantage of the residual net is you already have a wire that knows how to do that. You don't need to wait for anything to converge in order to compute the identity function. Therefore, actually combining ideas from Inception and ideas from ResNet is giving the best results right now. So they're non-redundant ideas. All right, I'll see you next time.